Okay. Share screen.
Good morning, Dr. Charity.
Good morning. How are you doing today?
I'm good. I'm actually at home for today, so got a
Okay,
different
great.
background.
Okay, I can see that. Good to see you.
All good. Oh, and it was kind of rough. I didn't realize that the assignment was due like 12 o'clock last night because I saw that it said Friday. So I was thinking like 12 o'clock today. So it's technically late. That was kind of rough.
Okay, but have you submitted yours?
Yeah. The
Okay.
assignment 2 or whatever it was called. Yeah.
Okay. Okay.
And I rewrote it all out just for you. So it was like even neater and everything. So
All right. Okay. All right. Good morning, everyone. I want to assume that everyone can hear me, right?
yep, I can at least.
Okay. Okay, so today we'll be talking about projectile motion, and we'll be discussing this neglecting air resistance. We're not going to factor air resistance in our discourse. So we're going to assume that all the objects we are looking at, we are able to ignore air resistance to the effect of their motion, okay? Projectile motion is an extension of two-dimensional motion of free fall, okay? We saw free fall motion, we saw acceleration at constant acceleration under free fall motion. And we practicalized that in our lab on Wednesday. We're able to see how that our measurements were close to what the standard value of G is. Okay, so the thing about projectile motion is that once you have a strategy to solving your problem, projectile motion problems, it applies to any kind of projectile motion you can think of. Okay, so a projectile motion is an object that moves in 2 dimensions under the influence of gravity and nothing else. Okay, we saw that in free fall, and that is why we're saying it's an extension of free fall motion. Okay, so we have a picture, a photograph in our first slide today. We have 2 balls, the red and the yellow ball. They are launched at the same time. But we can see that from this picture, the red ball was released just like what you did in the lab. You release the ball straight to go vertically downward. But we can see the yellow ball taking an horizontal motion and also going downward. Okay, so the red ball is under free fall motion and the yellow ball was shot horizontally. But the thing we should note here is that the vertical motion of the yellow ball still exists. And the vertical motion of the yellow ball has no effect on the horizontal motion, even though it was shot horizontally before it started falling, taking the free fall motion, okay? So for an object in projectile motion, the initial horizontal velocity has no influence. We should note that over the vertical motion and vice versa. And that is why we say it is a 2-dimensional motion, because we're able to describe its motion in the horizontal dimension, and we are able also to describe it in the vertical dimension. And we have seen this before when we talked about decomposition of motion. We decompose the velocity acceleration to the x, which is the horizontal, and the vertical, which is y axis. Okay, and we have the formula that we use the trig to find the angle of inclination in our last class. So it is worthy of note that the horizontal and the vertical component of any object undergoing projectile motion are independent of each other. So we should take note of this fact because we'll keep emphasizing this throughout our discuss today. Okay, so we'll have in this figure the projection of an object straight from a source and follow the curved path down. This is the initial velocity of the object, which can be decomposed or resolved into the y-axis and the x-axis. So let's take an example to drive home this point. We see a case of two balls rolling towards the edge of a table, with ball one rolling twice as fast as ball two. Both balls leave the edge of the table at the same time. Which ball hits the ground first? Which ball goes farther? Okay. Now the picture we saw earlier can also be presented in this kind of question. Okay. We see that there are two balls. One is rolling twice as fast as the other, but they both left the edge of the table at the same time. And the question is, which one will hit the ground first? Ordinarily, we would think that, yes, the one that is rolling as twice faster than the other will hit the ground first, but that's not the case, okay? Because the two of them will come under the projectile motion influence, and they will obey also the law of free fall, which means they will also go down at the same acceleration rate, okay? So where the difference will come in is in which one is rolling farther, because both will hit the ground at the same time. All right, and what is the reason? The vertical motion of both balls will be the same. Whenever we say vertical motion, we are referring to the motion that is pulling it down, the y-axis, okay? Both will be under the same influence of free fall, and they are falling from the same height. Remember what we said about objects, whether they are heavy or less, regardless of their mass, whenever they are undergoing a free fall, they fall at the same acceleration. So they will hit the ground at the same time interval. All right. But because the other one is moving as twice fast as the ball one, the ball one is rolling twice as fast as ball two, it will have a longer distance to cover in terms on the x-axis. Okay, so if the ball were to be dropped directly on the y-axis, you will see that the second ball will go farther away from the origin. Let's take the origin as 0. Okay, so it's going to look like something in this picture.
Would it look kind of like this, like I've drawn it out?
I didn't get you.
Would it look like if you looked at my camera, like would it look like this because I've drawn it out?
Okay, yes. That is exactly what I'm describing. So the other one will hit the ground at the closest to the height that is the vertical axis, while the one that is moving twice as fast will take a longer, I don't want to use the word range until we meet the discussion on range, okay? But we'll cover a longer distance, all right? So, but they will take, this will happen at the same time interval, all right? So because ball 2 is moving twice the same speed as ball 1, no, ball 2 has twice the horizontal speed as ball 1. It will cover twice the distance as ball 1. Okay, so we'll see the influence of the fast motion more on the horizontal than on the vertical. All right, so we have another one. This is just to emphasize, which we have seen before, the acceleration of projectile motion, okay? Because it's a kind of free fall motion, and we have discussed free fall intensively in our previous classes. We'll see that the acceleration will point downward. It's always pointing downward, even when the ball was going up. The acceleration is pointing downwards. So the motion of a tossed ball into the air before it took a curve, which is projectile motion, and hits the ground. We can see that, you know how we resolved this? We did this in our last class. With the change in V is always the acceleration. Acceleration is the rate of change of velocity with time, okay? So the change in V, we see change in V will give us V1, the V1 minus the V2, that is just reversing this to give you the minus. And then the resultant or net velocity will give you the acceleration, and it's always going to point downwards for each of the cases. Okay, so we see that the acceleration is the same for all the points. You can see the length of the vector representation arrow for the acceleration is the same at all points. And that is because for objects undergoing free fall, they fall at acceleration with magnitude g, which is 9.80. Okay, so the vertical component of the acceleration, ay, this y is not a capital Y, not the big Y, it's subscript there. Okay, for all projectile motion is similar to, always note this is not just negative g. The minus is pointing or emphasizing that the direction of acceleration is pointing downwards. Okay, but for the horizontal component, the S is 0. Okay, in both cases. So how do we analyze projectile motion? When analyzing projectile motion, we bring in understanding of acceleration of constant velocity. We bring in a constant acceleration on the vertical axis and then constant velocity on the horizontal axis. Our understanding of that is what we actually apply to analyzing projectile motion. So let's look at the figure A, the launch and motion of a projectile. You look at the ball, it was launched at an angle, which we'll call the launch angle, or we saw this kind of angle also when we were discussing the motion of a ramp, the inclination angle in that case. But in projectile language, we call it the launch angle, okay? So the launch angle, the ball was thrown at or launched at a particular angle. And we can see the initial velocity of the ball before it took the curve path. This initial velocity can actually be resolved into or decomposed into its y component and s component. And the y component, using we're able to prove how we got this in our previous class. So the s component vi cos theta and the y component vi sin theta. The launch theta is the launch angle, okay? So, but looking at the analysis that is putting values to this description here. Let's assume that we'll launch this at the ball at angle of 63 degrees, and it's moving with the initial velocity of 22.0 meter per second. Okay, we impute that into our equation. We will see that this will move at this velocity, and this is moving at this velocity. Okay, so we'll see that the velocity on each of the axes is independent of each other. But We should also note that projectile motion that is moving at, that is any object under projectile motion, the velocity on the x-axis when you decompose it, even when you know the velocity of launch, is going to be different from that of the y-axis, okay? We keep emphasizing this. The horizontal and the vertical component of a projectile motion are independent, but we analyze them as one motion because we will always need them to solve problems or determine the missing components by applying the kinematic equation for projectile motion using the kinematic equation of constant acceleration on the vertical and constant velocity on the horizontal. Okay, so if we look at the figure B before us, we'll try to project the same motion of this ball. Okay, we can see that at the horizontal, throughout the motion, the horizontal velocity was constant throughout the motion. But the vertical kept changing because it's going to be reducing by the value is undergoing free fall 9.8 until it gets to the point, start point, and immediately it gets to the start point and goes below the start point, the value changes to be negative. You see the arrow going down being the negative part of the arrow going up, but the x remained the same throughout the motion. So when the particle returns to this original height of launch, it turns to the opposite of its launch and it becomes negative. So y is opposite to the initial value, and that is why we'll have the same value, but the negative sign pointing us to the direction. Okay. So without the air resistance, displacement of an object is independent of its mass. We have emphasized this when we discussed the free fall. Okay, that the motion is independent of its mass. So how do we solve problems relating to projectile motion? What are the strategies we employ to solving these problems? We emphasize that once you can establish or understand a particular strategy, it applies to all, whether the projectile motion is a ball, a car, or whatever, no matter, regardless of the mass. The strategy you know will apply to all, okay? So we'll solve projectile motion problem considering the horizontal and the vertical motion as separate but related problems, okay? And what do? We follow a number of steps to do this. So let's look at the number of steps that will follow to solve projectile motion problems. So we start by making simplified assumptions. That is, we assume that all the objects can be represented with a model. No matter the size of the object, you can use a dot to represent it, be it car or a basketball. Okay, so you can make a picture diagram of what the motion is described as. So after you make the pictorial representation, you have to proceed to establishing a coordinate system that is defining your X and Y axis. Okay, if they are not stated in the question. So in this case, you know the horizontal acceleration is going to be 0. Many a times, the kind of motion we describe will give us horizontal acceleration as 0. Why? Because the acceleration is pointing downward. Acceleration of a free fall is on the y-axis. So ax is 0 because it's a free fall motion. And the acceleration is going to have the negative sign. So the g which describe the magnitude, to have a negative sign in front to emphasize that the motion is pointing downwards. So we do a vector representation using the components in terms of speed and also the angle of launch. This is very important because when it's given, you can use the information of the angle of launch to know the value for the X and the Y part of the velocity vector. Okay, so we also have to define our symbols and write it down clearly, because sometimes when we use D with an arrow and we use S to represent displacement, they don't mean the same thing. Okay, one is describing specifically a vector motion and one is describing change in speed. All right, so that is why it's important to define our symbols. So this equation that we are presenting in this slide, we have seen this kind of equation before, and we'll call them the kinematic equation describing position, acceleration at constant velocity, constant acceleration equation. So we adopted this kinematic equation for the previous discourse into the projectile motion. So it's the same thing, but the only thing that changed is the signs, and that is because acceleration for the projectile motion takes the same form as that of free fall, which is minus g. Remember, when I say minus g, I'm not referring to the value of g as minus. Okay, so the set of equation here describes the position and velocity, or displacement and velocity equation for the horizontal part of that motion, and we use this to obtain the vertical part. So in most cases, when we ask questions that relates to the range, the velocity in the S direction, we apply this to equation after using the first set of equation if the angle is given. That is the equation for resolving the component, resolving the vector into components. Okay, so we see that something is the same on the two sides of the equation. The time is the same for the horizontal and the vertical component. So we'll find change in time, or the difference in time, or change in t by solving the vertical problem or the horizontal component, depending on the one that applies to the question at hand. Okay. Okay. Are we together? I'm just talking to myself. Hello?
Yep, I think so, yeah.
Okay. Am I going too fast? We have so much to cover in this class. That's what I'm trying to make sure I did that. We are good. Good to hear that. Okay, so let's take another example. In this case with figure description now, not like the first example we saw. So we know the dog jumping game that will play with animals, all right? So in the sport of dog jumping, dogs run at full speed off the edge of a dog. Then they take a leap, they project or cover a distance. So the dog run at full speed off the edge of a dog that sits a few feet above the pool of water. The winning dog is the one that lands farthest from the end of the dog. That is the one that goes farther from this y-axis. So if a dog runs at 8.5 meters per second, okay, this is from research, is typically the speed of the dog in the dog jump, straight off the edge of the dog, and at this distance, about 2 feet from the standard height, and lands on the water, how far would the dog go before splashing down? Before it hits its final position, what is this? How far is it going to go from this origin? That's the question. So we'll try to bring out the parameters of from the information supplied in questions. And what we're actually looking at or looking for is how far, that's the distance that is going to go on from the origin, that is this distance covering this. I don't want to use the word range because we're to get to that. So let's be using the word distance. So what we did was adopt one of the equations we just displayed earlier, which we call the set of kinematic equations to describe position. And we're adopting the one we used to describe the vertical position, okay? Now the initial, from the information we have, we see that the initial velocity on the y-axis is 0. If you look at the diagram, the initial velocity on the y-axis is going to be resolved on this line. For this motion, it's going to be 0. Okay, because it's exactly straight on the x-axis. So we'll have our Vy initial to be 0. And we also have that it's substituting straight into the equation above. The Vy final, sorry. Vy final to be 0, Vy initial was stated in the question. Yeah, it's Vy initial. Okay. This takes this out. We omitted some steps here, which I know that is simple enough. We multiplied all these, took the roots to get this value. Okay. We made this the subject of formula, took the root of the final answer to get this value. Now, if this kind of question happens to come out in your exam or test, you're meant to show the missing step, please. Don't just say rearranging terms to solve change in S, we find no. Because if we are to draw the marking scheme or marking guide, this will have its mark, this will have its mark. About 3 lines that are not shown in this equation will have their marks, okay? So first, how did we get these lines that I'm saying we show? We made this the subject of formula, move this to this side, divide by the component of this, then take the root to get this. Okay, so having obtained the value for time, we now took the equation that described the distance on the horizontal axis, and that is the equation F final. You know, this came from velocity equal to change in S over change in time, okay? And you know that change in S is equal to S final minus S initial. All right, so when this is put here and you make this the subject of formula, you move this to this side. We have seen this equation and how we arrived at this before, all right? So from that definition, we're able to get the final distance. The initial was 0 at this point, and this was given to us in the question, which is the velocity on the x-axis from the initial, the dock motion from the start, and then the time to arrive at the fact that the dock was actually able to go 3 meters far from the edge of the dock. So that's how I applied those equations. So let's see a second example. We have a lot to cover, so let's go a little faster, all right? So in a soccer free kick, this one I'm sure we are very familiar with this kind of motion. The ball is stationary. Then the player comes, kicks the stationary ball toward the goalpost that is 18 meters away. I don't know if that's the standard measurement on the field, but anyway, it's 18 meters away from the goalpost. He kicks the ball at an angle of 22 degrees from the horizontal at a speed of 23 meters per second. That means the launch angle is actually 22 degrees. Okay. How long does the ball take to reach the goal? And how far off the ground? How far off the ground is the ball when it reaches the goal? Okay, so we'll have the picture of what we just described in words. Now, we're asked two questions there. How long does the ball take to reach the goal? This is the goal post. So we're not saying the ball entered into the, how long will it take to reach this? And how far off the ground is it going to go? From the definition or the specified angle of launch, which we know that two things influences a projectile motion, which is the angle of launch and the initial speed. The angle of launch and the initial speed. These are the two factors that determines the range of a projectile motion, which we will see when we start discussing range, okay? So resolving, because we have the information about the launch angle, and also we have the information about the kick, the velocity at which the ball took off the ground. We can actually use those two information to get y and x axis by decomposing this motion. All right. So we do that straight out from the information supplied. For the x-axis, we're going to get this, the velocity on the x-axis and the velocity on the y-axis. So since we have the velocity on the x-axis and the y-axis, we can adopt also the kinematic equation to find the parameters that we are looking for, which is our time and the distance, which is how far, right? Yes. Okay. So we adopted this to look for the time. We make T the subject of formula here. Making T the subject of formula, we have this. Either we'll move it to change in T, or because this is already established to be 0, it's just going to be XF equal to change in T. So if you make this the subject of formula, you have this. And impute the information you have, which is the final distance or the distance covered. So sorry, so this is just XI, not XI straight out, okay? So substituting it into this, the distance is 18 meters from the goalpost. And then we'll have our velocity as resolved from this equation. We are able to get the time that the ball will take, which is how long does the ball take to reach the goalpost. We know the distance is going to cover to the goalpost. We already know the velocity on that axis, so we're able to get the time to be 0.845 seconds. So once we solve from the information of the time, we can solve the second question, which is how far off the ground the ball is going to be. And how far off the ground will give us the vertical position. That means we adopt the equation on the vertical. We'll have two sets of equations. Whenever we're solving problem relating to the vertical, we pick an equation there to adopt. Whenever we're solving problem relating to the horizontal, we'll pick an equation on the horizontal part of the equation set to apply. but we use the resolution of or the composition of the vector in both cases, okay, depending on how the question is asked. So imputing directly our parameters into this equation of a position, and remember this is the same thing as the equation of position for constant acceleration, which we said earlier that we'll be applying the equation of position for constant acceleration on the vertical and for constant velocity on the horizontal, okay? So when we imputed that into our equation, we're able to find that the distance of the ground was 3.8 meters, all right? Okay, we have less than how many minutes? So let's go fast. We want to discuss the range of a projectile. What do we mean by the range? There's no way you can describe a projectile motion without describing angle of launch and range, okay? Because they are the two important factors that will help you analyze the motion. So when we say range of a projectile motion, what are we talking about? We're talking about the distance that the object is going to cover or travel on the horizontal axis, okay? That is on the x-axis. So range is always determined by two things: the initial speed and the angle of launch. The initial speed and the angle of launch. This is what determines the range of any projectile motion. Okay, and this is what they put to play in the sport of golf and then long jump or whatever sport that involves the motion of a projectile. Okay, so we have in the figure before us the range of, let's say, a ball that was launched with different angle, but they are moving at the same initial speed. Remember, we said the angle of launch and the speed will define the range. So now let's look at this. We have already established that the launch of this ball from the origin is at the same speed. But look at the different angle. When we launched at angle 15, it landed somewhere around, say, 500 meters. Now we launched at angle 30. You notice it went farther. We launched at angle 45, which is the farthest. Angle 45 is the maximum range that is achievable theoretically. Sometimes in real life, because of the air resistant factor, it's a bit less than 45, but neglecting air resistance, the maximum angle that will give you the maximum range or travel distance is 45 degrees. Okay, so let's look at when we launch at angle 60, we see that angle 30 and angle 60 landed at the same point. Angle 15 and angle 75 landed at the same point. What is this telling us? That when the angle is too small or too high, the range is going to be small. Okay, and so too high, too low angle will give us a small range. But when the angle is close to 45 or a little above 45, you're going to about the same distance. But when you are able to project at an angle very close to 45, you project the farthest. You'll be able to cover the farthest distance. So we'll see that the angle of launch is determining the y-axis, how far off the ground the ball or whatever object that is being launched is going. Okay, so let's see this Let's pause a little before we go to the last two subjects we'll be talking about today. We have an example before us, two balls. Okay, so let's look at the circular motion. Now, if we take a good look at the picture of the circular motion before us, let's take closer look at the vector, the velocity vector arrows. What can we say about the velocity vector arrows? They are all of the same size. And what does that emphasize to us? That the speed is constant, okay? We can see that this kind of circular motion can actually describe a uniform motion because the arrows that describe the velocity vector, they are all of the same size. So it means this circular motion is actually a uniform motion in a circular form, okay? And we are encouraged to look at this section that describes the object whose velocity is changing, but that is changing, the velocity is changing and has acceleration, but actually it is moving at a constant speed, okay? So the same way we look for acceleration, how did we establish that? We have seen before the motion on a curved path where the acceleration is always pointing towards the center. So now we have a motion in a complete circular form, which describes the motion of what we see some roller coasters we see in one of our examples. It could be on the vertical circular or horizontal circular, no matter what direction it is, but the motion is moving in a circular form. And we can see the acceleration vector all pointing inward towards the center. So as the motion is taking a circular path, acceleration is pointing or coming to the center. Just to establish that the acceleration is coming to the center, let's take the definition of acceleration, which is change in v over t. Okay, so change in v describing v2, motion of v2, we bring the v2, minus v1. Just reverse this. You know the way we did it in the vector representation. Reverse this to give you this line. Give the two, make a diagram of the resultant or net velocity, which will give you the change in velocity, which is the acceleration. Change in v is the acceleration. So you see the acceleration of this point points into the center. If you take these two, do the same thing, it's going to point this way. So we'll have that all the acceleration is pointing towards the center. Okay, so what you should note about this is that the acceleration is pointing towards the center. And when we have the acceleration that's always pointed directly towards the center of a circle, we call that kind of acceleration centripetal acceleration. Centripetal acceleration is the acceleration pointing towards the center of a circle. And it came from the Greek word center. The word centripetal came from the Greek root word center. Okay, so anytime you think of the beginning, center, centripetal force or centripetal acceleration, we're talking about acceleration or force directed towards the center of a circle. Okay, now that we have described acceleration, introducing an acceleration that is directed towards the center. We have seen different form of acceleration now. We saw the one that can be described with the direction. We saw the one under the influence of free fall. We are seeing another one now that is directed towards the center. Okay, so the centripetal acceleration, the free fall acceleration, and then the acceleration on plane, either two-dimensional or single dimension plane. Now, the unique thing about these three forms of acceleration that we have seen is that we are adopting the same idea or understanding of the definition of acceleration, which is change in velocity with time. Okay. So in the description of circular motion, we adopted the same idea, but we had slight change because we are describing the distance, and with respect to time in this case, we're going to be using the radius of that circle we are describing to define or specify a kind of time range or distance covered. Okay, so let's see this equation that I circled here is the established equation for acceleration under the centripetal acceleration influence. That is, acceleration that is pointing towards the center of a circle is described with the equation v squared over r. Okay. So to complete our discussion, we're just going to look at how we can find a quantitative relationship of this magnitude of acceleration to speed, which is established by this. How did we arrive at this? That is deriving this equation from our understanding of the circular motion, the v, and the acceleration pointing to the center. We can see something unique about the v and the acceleration. The velocity is always tangent to the circle. Okay, you can see that when you try to make this one a perfect circle, you see the velocity having a tangent position to the circle. Okay. Then the acceleration is what? Perpendicular to that circle.
Because isn't that why, like, when you take a turn and with a car, like, you always feel like you're going through the door?
Yes. You feel like you're leaving the car, you're going away from the car to the door. And that is what the belt will help you to keep you in position in the car, the seat belt. Okay. So someone, inertia, yeah. That describes inertia. We'll see that in our chapter 4, when we start talking about motion. We'll also relate this to inertia. You don't want to change position, you want to continue at the same rate you're going. Okay, so that is what we experience in circular motion. Okay, so we have just 3 minutes to cover about 5 slides. These steps is just the proof of how we arrive at this first equation that we established as the equation describing the acceleration of a circular motion. Okay, so what we did was to cut parts of this circular motion. We described the radius from the middle of the circle, the length. You see it better by cutting this. Okay, making the perfect circle. You see how the velocity will make a tangent to that circle. Okay, so if you have the understanding that velocity is making this tangent, and you can combine these two velocities to form the acceleration, and it will point perpendicular to that tangent. We have the displacement is just the description of v without the vector sign. So when we use this v, we're talking about speed, okay? And when we use the other v, we're talking about the vector, okay? So d here also mean, from this equation, v equal to x, you can write it as d change in time. dx describes the displacement, okay? So that is the equation we have here. describing this with the displacement and substituting this into this first equation. That is where you have D, put this one there. If you do that, you have this expression. Rearranging this, we will have that the change in V over change in T, which we recognize as the definition of acceleration, is equal to V squared, this multiplied by this, okay, over R, and A is not equal to this expression, okay. So that is how we arrived at this. Let's quickly take one example, then discuss the last one, which is leave the example, you study that. Just 1 minute extra, please. Relative motion. Now, the important thing to note about relative motion is the description of motion relative to a frame of reference, okay? So we'll have three, in this example, we have the runner. Bill, Emmy, and Carlos want to describe this runner. Bill said that the runner is running at velocity 0. But Emmy, because Bill and the runner, they are moving at the same speed towards the same direction. So they are always together. So it appears as if nothing is changing. So their velocity is 0. But Emmy is stationary, standing. It saw the velocity of the runner to be 5. Now there's a car that is moving faster than the runner. The car is going to see that the runner is retarding, that is, the runner is going back or decelerating instead of moving forward together. So it's going to describe the runner speed as minus 10 meters per second. Now the minus is showing that the runner is actually going backward while the car is projecting. Now the question is, which of these have the true description of the velocity of the runner? The answer is that each of them is correct in terms of frame of reference, because each of them describe the runner speed relative to their own frame. So whenever we talk about relative motion, we are talking about motion that you can describe relative to a frame of reference or reference frame, okay? So the point we want to establish here is that if you have several frames of references, we can actually describe the motion in respect to a particular frame of reference to get the value. We have been describing motion without putting in the factor that we are describing this motion without specifying a reference frame. So we'll have cases where we have to describe a particular motion relative to a reference frame, or describe the velocity of an object relative to the observer that is taking the measurement, which we will see in the last example that I will leave for you to study on your own. So but what we want to establish is that from the idea of relative motion, we can actually bring in relative velocity to describe the velocity of an object if we know the reference frame of an observer, and we know the speed of the object relative to the reference frame. We can actually reach an equation that helps us find the reference frame, the velocity in the reference frame that we are looking for. If we have the information for Amy, we have the information for Carlos, we can actually get the information for the runner and Carlos. So we have runner and Amy and Carlos, and we can, from these two relationships, obtain runner and Carlos. Okay, and that is emphasized here also. Let's use another scenario. This car, the runner, and the ground. We have the car, the runner, and the ground. Everybody is moving on the ground. We want to describe this relative to the ground. Okay, so we'll have the speed of the car relative to the runner. Because we can describe both motion relative to the ground, we have car to ground plus ground to runner. okay, to obtain this. So if you are given 3 speed, you can actually, here, we see that we eliminated these 2 to get this. Okay, these 2 goes as well. So this is serving like, I don't want to use the word interface for both, okay, but it's the idea of the interface. This relates to this and it relates to this. Therefore, we can relate this one, these 2 together. Okay. So I'd like you to study this example. The example we skipped here, I'll put it in the assignment to study the examples that we skipped and also show the expression of the steps that were omitted just to drive home the points we have made in class today. Okay. So by next week, we'll begin with our chapter 4, which is Newton laws of motion and how we apply them to solving problems. Okay. I also encourage us to practice the quiz. I didn't put them on Moodle because I already have them here in our end of chapter 4. We'll take a quiz on Moodle as well. All right. Okay. You can send me your questions or comments either on email or text or in person. All right. Okay. Thank you so much. So are we together? Does anyone have any comment to make before we end the clock?
Thank you.
Yep. All right.
Goodbye.
Goodbye. Have a great weekend. Bye-bye.
You too.
Yeah.
Thank you.
Okay.